Simple linear regression is a statistical technique used to model the relationship between two variables, where one of the variable is the independent variable, which is also known as the predictor variable, while the other variable is the dependent variable, which is also known as the response variable. Simple linear regression helps us understand how changes in the independent variable affects the dependent variable. In simple linear regression model, the relationship between the independent and the dependent variable is represented by a straight line equation. Here you can see that we have the mathematical representation of our regression model. In this equation, y is the dependent variable, whereas x is our independent variable. We have two parameters here, beta naught and beta 1. And we need to estimate the values of these parameters using econometric techniques. We have another term in our equation, epsilon, which is called the error term or the residual term. Error term accounts for the unexplained variation or noise in the data that is not captured by the regression equation. In simple words, it represents the difference between the predicted values of the dependent variable and the actual observed values. These differences can arise due to various factors such as measurement error, omitted variable bias, or inherent randomness in the data, or also due to wrong functional form of the model. The inclusion of the error term makes the regression model more realistic because not all variations in the dependent variable can be perfectly explained by the independent variables. Now we are going to discuss the estimation technique which is called ordinary least square, OLS. The primary goal of the regression analysis is to find the best fitting line that minimizes the difference between the predicted values of the dependent variable and the actual observed values. In a regression line, beta naught is the intercept and beta 1 is the slope. Intercept is the point on y-axis from where the graph of a line begins, while slope tells us the direction and steepness of the line. If you could estimate these two values, beta naught and beta 1, you can easily draw the regression line. To estimate these values, we use the technique called OLS, which minimizes the sum of squared errors. Here in this graph, you can see that the line is starting from this point. So here we have our intercept, beta naught, whereas the sign of the slope is negative, which shows that the line will be sloping downward. However, if you have positive sign or positive value of the slope, the line will move upwards. So in simple words, the sign of slope tells you about the direction of line. However, the magnitude of beta 1 tells us the steepness. If the value of beta 1 is exactly equals to 1, your graph will move along 45-degree line. If value of beta 1 is positive, the graph will be steeper, and if the value of beta 1 is less than 1, the graph will be flatter. Now we are going to understand the concept of OLS through an example, then we would derive the formula of beta naught and beta 1. Suppose that you have collected data on income and consumption of 5 households where consumption is our dependent variable represented by y and income is our independent variable represented by x. Here we have plotted our sample observations on a scatter plot, and we aim to find a line that best represents these scattered dots, capturing the essence of our observations. But here you can see that multiple lines can pass through the scatter plot. To determine the best fitting line, we need to establish a criterion. Let's assume that the criterion is that the line is best when the difference between the estimated values and the actual observed values is minimized along the line. In simple words, the best fitting line is the one that minimizes the sum of errors. Here you should know that error is the difference between actual values of y and estimated values of y. To make it simple, suppose that we have just two lines on the scatter plot. Red and blue. Let's discuss the red line first. At x equals to 10, the actual value is 6, while the value on red line is 6.5 at x equals to 10. The difference between these two values is error, and you can see that the difference between these two is minus 0.5. At x equals to 20, the actual value located on dot is 21, while the predicted value at x equals to 20 along the red line is 17. So the difference between the actual and estimated value at x equals to 20 is 4. Similarly, the process of calculating error is repeated for each value of x, and then we will sum the errors. Here you can see that when we sum the errors for the red line, the sum of error is 0. The same process is done for the blue line as well. We have calculated the difference between actual and estimated values for the blue line as well, and you can see that we have errors here, and when we sum the error, we also have sum equals to 0 for blue line as well. Here you can notice that despite apparent differences between the actual and predicted values on the graph, the sum of errors are 0 for both red and blue lines. The reason for this lies in the positive and negative sign of errors cancelling each other out, resulting in a zero sum. Thus, the criterion of minimizing the sum of errors proves ineffective. To address this issue, we need to revise our criterion now. The problem in this criterion stems from the sign of the errors, and to overcome this, we need to adopt a different approach now. Now we have decided to square the errors, which eliminates the negative sign while preserving the magnitude of the differences between the actual and predicted values at each x value. Now our revised criterion for the best line is as follows. A line is best if it minimizes the sum of squared errors. Thus, using this criterion, we will derive the formula of parameters beta naught and beta 1. This approach is called ordinary least square. Least means minimize, square means square root of residuals. So in other words, in this approach, we will be minimizing sum of squared residuals. Let's start this derivation of all estimators. As you know that the criterion for the best line is to minimize sum of squared errors. We have the mathematical expression for it, and we have written it as minimize sum of squared errors, where error is the difference between actual values y and the estimated values represented by y hat. If we put second equation into first, we get the following equation, and let we name it equation 3. Since y hat is the value on regression line, y hat would be equals to beta naught plus beta 1x, which is the equation of line. Now put equation 4 into equation 3 and we get the following equation. Remember that in mathematics, when seeking to minimize or maximize a function, we employ first order condition and second order condition. In first order condition, we take the derivative of the function with respect to the variable or parameter we want to find the value for, and then set the resulting derivative equal to 0. This process yields the solution of the unknown value. In our case, because we are interested in finding the value of the parameter beta naught and beta 1, so we would be taking derivative of equation 5 with respect to beta naught and beta 1, and then we will set the resulting derivative equals to 0. In this way, we would get the solution for beta naught and beta 1. while the second order condition is applied to confirm whether the function is maximized or minimized at the solution value. Let's apply first order condition with respect to beta naught and beta 1 on equation 5. I am taking derivative of equation 5 with respect to beta naught first. This is how we take derivative. Bring the pi into base, write the function and subtract 1 from the power. So when we subtract 1 from 2, we get 1 here. So we don't need to mention 1 here. So again I am repeating. Bring the pi into base, write the function, subtract 1 from the power, then take the derivative of the function without power. Now I have taken derivative of the function inside the bracket here. In the first term we do not have beta naught, so derivative of this term is 0. In the second term we have beta naught, so its derivative is -1. And in the third term we do not have beta naught, so its derivative will also be 0. So derivative of the terms inside the bracket is -1. Now take -2 to another side of equality, and anything divided by 0, or in simple words, whenever we have 0 in the numerator, the whole value becomes 0. So we have 0 here. Now apply summation to the terms inside the bracket. Y and x are variables, you already know that, and beta naught and beta 1 are the parameters, and we have just a single value for these parameters. So in other words, beta naught and beta 1 are the constant values, and whenever we apply sum to a constant term we get n here, right? So we have summation y minus n beta naught minus beta 1 summation x. When you are having a constant term with variable, and when you are applying summation to that term, summation will be applied to the variable only. So here we have got equation A by taking derivative of equation 5 with respect to beta naught. Now I'm going to take derivative of equation 5 with respect to beta 1. Here bring the pi into base, write the function, subtract 1 from the power, and take derivative of the function without power with respect to beta 1. Here you can see that in the first term we do not have beta 1, derivative of the first term is 0. In the second term we do not have beta 1, so its derivative will also be 0. In the third term we do have beta 1, so derivative of beta 1 with respect to beta 1 will be equals to 1. So we are left with just minus x in the bracket. Again take -2 to another side of equality, and we would have 0 on right hand side of the equation. Now multiply x with all the terms inside the bracket. You have to multiply x with y, then beta naught, then beta 1x, and then apply summation. So in this way, after applying summation, we have got equation B. Here is our equation A, and here we have our equation B. Now we have to solve equation A and B simultaneously to get the solution for beta naught and beta 1. So here we have equation A and B. Now we are going to solve them simultaneously. I'm using the elimination method. Here I want to eliminate beta naught from equation A and B. For that you can see that in equation A I have n with beta naught, and in equation B I have summation x with beta naught. So I will multiply equation A by summation x and equation B by n. Here I have multiplied equation B with n and A by summation x. Now I am going to subtract them, and here you can see that these two terms will be cancelled out. We are left with these terms now. As you know that we are interested in finding the value of beta 1 here, so I'm going to take the terms having beta 1 on right hand side of the equation. Now I'm going to take beta 1 common. and take the terms with beta 1 to another side of equality. So here I have got the formula for beta 1. Here first of all I have simplified equation A. I have taken the beta naught term to another side of equality, and then I have substituted the value of beta 1 into this equation. Now I'm going to take LCM of this equation. Here is the LCM, and now multiply summation y with the terms inside the bracket and minus summation x with the terms inside the brackets here. After multiplication, you can see that we have got two similar terms with opposite signs. These two will be cancelled out. So we are left with two terms in the numerator. You can see that both the terms in the numerator have n, so we can take n common. Now cancel out n from both sides, and we are left with the following terms. So this is the formula of beta naught. Using these two formulas, we can estimate the values of beta naught and beta 1 subject to the availability of data on x and y. We have an alternate formula for beta naught as well, and the formula is as follows. Beta naught is equals to y bar minus beta 1 x bar. Y bar is the mean value of y, and x bar is the mean value of x variable. And first of all, you have to calculate beta 1 and then substitute the value of beta 1 here to calculate beta naught. Suppose that we have the following sample, and we have 4 observations, and to apply these two formulas we need to have n is here 4, the sample size. Then we have to calculate summation xy, that is we need to multiply x with y then sum it. We need to have summation x, we need to have summation y, and we need to have summation x square, that is we have to square x variable first then take its square. Here I am going to multiply x and y in the third column, and then I'll take square of x variable in the fourth column. Now we have to sum the columns one by one. Sum of y is 18 here, sum of x is 24, sum of x into y is 125, and sum of x square is 158. Now I will substitute these values into the formula of beta 1. After simplifying it, we get 1.214, which is the slope value, and you can see that the value is positive, so our regression line will be sloping upwards. Now I'm going to substitute the values into the formula of beta naught, and the value we have got for the intercept is minus 2.785, which shows that the line is starting from negative y-axis. Let's move to the interpretation of all its coefficients. The slope coefficient beta 1 represents the change in the dependent variable for 1 unit change in the independent variable, whereas the intercept coefficient beta naught represents the predicted y value when x value is 0. In our case, beta 1 is 1.214, which shows that when x increases by 1 unit, the dependent variable increases by, because we have positive sign here, when x increases by 1 unit, dependent variable increases by 1.214 units. Whereas the predicted value of y is minus 2.784 if x value is 0. This is how we write our regression line, and in this regression line, if we put x equals to 0, y would be minus 2.785.